Hey everyone, so this will be the second video on the whole gases series. And in the last one, we talked a lot about when you have like all these gas laws and how you can like change pressure, volume, temperature, and moles, and how that like impacts other properties of the gas. But really with those equations, those are great, but they kind of have some limitations to it if you think about it. We really only ever talked about having one gas. Like in the practice problems, we talked about having like hydrogen gas and diborane gas, but we never really thought about how in a lot of other cases, you get like mixtures of gases, like in a lot of reactions you run, you'll get like mixtures, or even just like in the real world, like gases tend to mix together. So then how do we study changes in gases when you have various ones? Thankfully, Dalton was a chemist who sort of studied this property, and he really looked at having mixtures of gases and what we can say for certain about them. Granted, it's a little bit harder to say for certain, but his equations do give some help in figuring out like the pressure of different gases and how their ratios matter. So we're going to talk about that for today. Um, so the first thing I want to talk about is really just like how we arrive to what Dalton's law is. So when we talk about having a pressure in a gas chamber, we can describe that pressure as just being the sum of all the pressures of the gases inside that chamber. So it doesn't matter how many you have. We can have one gas, two gas, three gases. It really doesn't matter. It's just saying that, the total is the sum of its parts. So that pressure in that system has to be coming from somewhere. It has to come from all those gases we have. And so this is now where we're going to use the ideal gas law again, because we know that with ideal gas law, we can describe um, pressure, volume, moles, and temperature. So we're going to, again, think about what you're keeping constant and what is changing. So if we have a system that's fully closed, the volume shouldn't be changing, right? We're going to keep that system as it is. And we just want to figure out what the pressure is of these different gases in that system. So volume won't change and temperature won't change, but the moles will be different. Moles of one gas will be different from moles of the other gas. So what we want to do then is see how pressure and moles are related in this case. So we'll divide by V to isolate just the pressure, and we can get that the pressure of any gas should be nRT over V. And now we can plug this in down here and say that the total pressure should be equal to the total moles in the system, RT over V. And again, as I said, the temperature is constant and the volume will be constant. I'll just rewrite that here. Those are going to be constant. So we can factor out just the n and see what that is. See what that is. So we have that the n total should be equal to, oh, sorry, n total um, multiplied by RTV. Awesome. And what we want to do next, and think about the same thing. If we have a total number of moles in our system, those moles come from somewhere, right? They come from the gases you have in there. It doesn't matter if there's one gas, two gases, or three gases. This has to then be equal to just those moles of gas A. Remembering the RT over V plus the moles of gas B times this RTV term, and so on and so on. So we had that similar relationship here where pressure was dependent only on the little parts you have from different gases. Same is true for the moles. So what we get here is that when you have a constant temperature and constant volume system, that the pressure depends on moles, or it depends on N. There we go. And so now that the next term I want to introduce about Dalton's law is something called a mole fraction, which has this Greek letter chi. I think this is chi at least. So the mole fraction of any gas is basically just the ratio that tells you how much of this chamber is that gas, or how much percent does this gas make up the full volume, the full quantity of gas. So that's equal to the gas you're looking at divided by all the moles in the system. So this is going to be the ratio of a gas, we'll say ratio of moles of a gas to total moles of gas in the system. So we have that. And now one thing keep in mind too, if we look at all these equations we talked about above, we can see that moles of gas and its pressure are directly correlated. So to say that the mole fraction is equal to the number of moles of that gas over the total moles is the same thing as saying that this has to be equal to the partial pressure of that gas, or how much pressure that gas exerts in the system divided by the total pressure in the entire system. And so now if we isolate just for that pressure of the gas, that's really what we want to find. We eventually want to be able to say, if I have four gases in this system, how much pressure does just hydrogen exert in this system? So if you want to find that, we just multiply by the total pressure, and you find that the partial pressure of a gas will be equal to the total pressure in that system multiplied by the mole fraction, or what ratio of the total moles does this one gas contribute to. So we had that. Honestly, that's really it for Dalton's law. I wanted to do a little bit less lecturing, just a little bit more problem solving on this one. So in a practice problem we have, we're going to have a mixture of methane gas and oxygen gas, and these are going to be at 0.175 atm and 0.25 atms respectively. So we're going to write down first that the pressure of CH4 is going to be equal to 0.175 atms, and the pressure of O2 will be equal to 0.250 atms. All right, awesome. First we can go ahead and figure out just what is the, you know what? I'll slow down. For this problem, for at least part A, we want to figure out the mole fraction of each gas. Now, there is a direct way, if you remember that pressure and moles are directly correlated, and there's more of a roundabout way. So we know that the mole fraction of a gas will be equal to the amount of moles you have of that gas divided by the total moles, but we also know this is equal to the partial pressure of that gas divided by the total pressure, right? So we don't need to go about finding out how many moles of methane we have or how many moles of O2 we have. You could do it. You absolutely could if you want to go through the process of it, but we would need some more information, right? We need to know how big this container is. We know the temperature of it most likely. So it's just not feasible to figure out what we have. So we need to go about using the partial pressure of these gases. So we can figure out the total pressure by adding together the pressure of O2 and the pressure of CH4. And so this will be equal to 0.175 atm plus 0.250 atms. And this will be equal to like 0.425. Yeah, 0.425 atms. All right, awesome. Now we have the total pressure and the pressures of each gases, we can figure out the mole fraction. So mole fraction of CH4 will be equal to 0.250 atms divided by 0.425 atms. Notice here mole fraction is a value that has no unit, because when you plug in atms over atms or moles over moles, it cancels out fully. So you won't ever have a unit for your mole fraction. It's just like a ratio, really. So we get for CH4 should be 0.588, and the partial pressure of O2 very similarly will be, dang, I'm sorry, guys. I realized I just did that wrong. So I accidentally used the pressure of O2 here in for CH4. So I'm just gonna erase that and just put down here, this is the mole fraction of O2. Yeah, I'm sorry about that. And that this one will be the partial pressure of CH4. Awesome. So now doing this out properly, the mole fraction of methane will be 0.175 atms over 0.250 atms. And this value will be equal to 0.412. Awesome. And if you notice too, if you were to take the pressure of O2, sorry, the mole fraction of O2 and add up the mole fraction of CH4, it equals 1. which makes sense because all we did was just say the total pressure divided by total pressure. It has to be one. You need to have a full pressure accounted for. So if these values that you find for the mole fraction of all your gases, if they don't equal one, it probably means that you either added something wrong or you might have like forgotten a gas or something, but it should always equal one whenever you find the mole fraction for all your gases. All right, so moving on, the next part says that if we now have a volume of 10.5 liters at this temperature, we need to find the moles of the gas. Okay, so for B, we're going to again keep in mind that we have information on volume and temperature, and we have the pressures. And so we have three pieces of information, and we need to find moles. So knowing all that, the best equation to use here is ideal gas law. It will almost always be ideal gas law. So, when in doubt, it's usually a pretty safe bet to use this. And we need to figure out what the N is. So we're going to go ahead and divide by PV divide by RT on both sides. And we're going to find that the moles should be equal to pressure times volume divided by RT. So what we can do here is say, oh, I'm going to move this over. So we can go ahead and say that the moles of CH4 is going to be equal to the pressure of CH4 times volume of the whole system divided by RT, and that the moles of O2 will be equal to the pressure of O2 times the volume divided by RT. All right, so we can just do that down here. Now, we gotta make sure we have the right units for everything. Always check that before you plug in any value. So for R, it's a constant. We already have that checked off. Pressure, we had that in ATMs. That's awesome. Volume is in liters. That's great. It's temperature though. So temperature is 65 Celsius. We need it in kelvins first. So the temperature that we have is 65 degrees Celsius. So we just need to add 273 to that. So that's going to be 338 kelvins. All right, now that we have that, we can actually figure out what the moles of these are. So moles of CH4 is equal to 0.175 ATMs from the last part times the volume, which is 10.5 liters. Now divide that by 0.08206 liters times ATMs over mole times Kelvin, and then times temperature, so that's 338 Kelvin. And this will give us 6.6 times 10 to the negative second moles. Awesome. And now we're just going to repeat the same process for the moles of the oxygen. So moles of oxygen will be equal to, instead of the pressure pressure of 0.175, we're going to use pressure of 0.250 ATMs times 10.5 liters. And then we're going to divide that by the universal gas constant again. 6 liters times ATMs over mole times Kelvin. And then multiply this by the temperature, which is 338 Kelvin. And with this, we find that the moles of oxygen is 9.5 times 10 to the negative second moles. Now, one good thing to always do is see if the answers you get make sense. So from this problem, we already know that the oxygen exerts more pressure because in part A, it said oxygen had a partial pressure of 0.25 ATMs, and that's more than CH4. So we would expect to have more moles of oxygen present. And that makes sense because in part B, we find that we have a little bit more moles of oxygen. So whenever you have a chance, like on exam or even just on practice problems, like ask yourself if what you got makes sense based on what you know about the equations or based on the problem itself. If it doesn't, try revisiting your math, see if you might have forgotten a zero, if you might have maybe divided something incorrectly. Just see if you can figure out what went wrong. Usually it's the temperature being in Celsius, but anything can happen. All right, so for part C of this problem, we need to figure out the grams of each gas. So for this, you really just want to use the fact that the mass of something in grams is going to be equal to the number of moles you have. So moles in N multiplied that by the molar mass, which molar mass basically tells you how many grams of substance there are per mole of it. So using this, we can find that the grams of methane will be equal to the moles we found, so 6.6 times 10 to the negative second times 16. And this will give you 1.06 grams, and that the grams of oxygen is going to be equal to 9.5 times 10 to the negative second times 16. And this is going to equal 1.51 grams. All right, awesome. So that's basically it for that problem. There really isn't much else to doing this, figuring out grams. Once you have moles, it's usually pretty straightforward. And again, if people want like an explanation on like how I figure out molar mass, I can definitely talk about that. But that's probably something I would do in a separate video instead of adding on to this one. So yeah, we're gonna do one more practice problem that I thought was kind of cool when I saw it. Um, so for this problem, we're taking a solid, so it's a salt, which is really cool. You're going to heat it. It's going to decompose into a different chloride salt. So you're going to take calcium chlorate, or sorry, calcium chlorate, and it's going to make you potassium chloride and oxygen. So basically, with this, we're going to observe that this gas formation is going to displace some water, and we're going to collect that gas, and we need to figure out how much oxygen we were able to get from it, and how much mass of the salt we had to use in the process to make that oxygen gas. So for this again, we just want to figure out first what the total pressure is, or what the pressure of the different things in the system are. So the total pressure in this has to come from the oxygen since we're forming that in the process. But it also is going to come from the water too, because it tells us here that the vapor pressure of the water is 21 torr. So it's at least telling us that the pressure of the water is relevant here. So we're also need to take into consideration how much pressure the water exerts in the system. So knowing this, we already know what the total pressure is. It told us the total pressure is 754 torr, and the pressure of H2O is equal to 21 torr. So with that, we just really need to figure out what the pressure of the oxygen is, and that's the most important thing here. So the pressure of the O2 would be equal to the pressure total in the system minus the pressure of the water we have. So if you do that, if you take 754 torr and subtract 21 torr, we're going to get 733 torr. And now this is why in the last video I gave you like all the conversions, since like does it suck to give it to you in torr instead of ATM? Yeah, it's kind of stupid. But whatever. I mean, it's not that big of a deal to convert them. So to go from torrs into ATM, you want to divide by 760. And this will give you an answer of about like 0.96 ATMs. All right. So we have that. Awesome. And what we want, so we already have the partial pressure of O2 that we collected. We got this much. Or if you want to say we got this much. I prefer to get my answers in ATM since that's just like what I'm used to doing, but you really don't have to for this problem right away, at least. So what we need to figure out now is the mass of of the potassium chlorate that we had to consume in this process to make that oxygen we collected. And now this is kind of like a weird thing because like it doesn't really relate to what we've been talking about with gases, but this kind of beauty of them is that you can take any reaction that either forms or consumes gases and study how the reaction proceeds just based on these gas laws. So what we want to figure out then is not the amount of mass we consume, since we can't go from pressure of oxygen into moles of potassium chlorate. You want to figure out just like how do you relate these things? Like what would make sense? Um, what we can talk about is the molar ratios of these in the reaction. If you look at the reaction, for every 2 moles of this solid salt that we react initially, we will get 3 moles of oxygen, right? It's a 2 to 3 ratio. So we're going to be gaining oxygen as this proceeds. The reason that matters is if I knew how many moles of oxygen I make, I can figure out the amount of moles of the potassium chlorate had to have been consumed to get that much oxygen produced, assuming it was a fully efficient reaction. we can assume that because it doesn't tell me anything about percent yield or the efficiency. So because that wasn't mentioned, I can assume it was a fully perfect system and not worry about that. So what we need to figure out now is how do we get moles of oxygen? And that's the main thing. Once we get that, it's pretty easy after that. Well, to figure out the moles of oxygen, we need to use ideal gas law. Again, it's like the best equation ever for gases because it works in so many different cases. So what we have is that the pressure of this O2 times the volume has to be equal to the moles of O2 RT. If I only want to look at the moles of oxygen, right? And this is why we needed the partial pressure of oxygen, because there was no way to figure out the amount of moles of just the one gas if I had a mixture of the water and the oxygen present. So with this, I would just go ahead and divide by RT like we did in the previous problem. And we need to find that the moles of O2 is equal to the pressure of O2 times the volume divided by RT. So this will be equal to, if we take 0.96 ATM, this is a good reason why I always make my answers into like the proper units if I have the time for it, because like it might be helpful later on. So 0.96 ATMs times 0.650 liters divided by the R constant. So that's going to be 0.08206 liters times ATMs divided by mole Kelvin. And now times the temperature, which I forgot to convert. So whenever you get to temperature, make sure you have that in Kelvin written down, ready to go. So the temperature in this case was 22 degrees Celsius. We can't use Celsius, so you have to make that into kelvins. How do you do that? You add 273 to that. So this is equal to 295 kelvins. And now we can plug that into here. All right, so we got that. And if you do the math out, you'll find that the moles of oxygen are equal to 2.95-ish times 10 to the negative second moles. All right, so now we have the moles of oxygen that we made in this reaction. And because we have the fully balanced equation, we can just look at that and say, okay, if I got this amount of oxygen to be made, it had to come from this amount of potassium chlorate. So to look at the reaction, we see that there are 3 moles of oxygen in the products, 3 mole O2. And how many moles of the solid that we want to look at were reacted? There were 2 moles. So there were 2 moles of KClO3. If you ever have a question about like which one do you put in the numerator versus denominator, just ask yourself what units you want to cancel out. This number we got over here, it's in units of moles of oxygen. So if I want to cancel out properly in order to keep doing the math, I need to divide it by moles of oxygen. So that's why I know it has to be in the denominator. So I'll do this in red. This cancels out. Awesome. And now keep in mind, the question did not ask for moles of potassium chlorate. It said specifically the grams that we collected of it, or sorry, the grams that, or the mass you had to decompose of it. So because of that, we need to then cancel out the moles. So how many grams are in a mole of potassium chlorate? I already wrote it down ahead of time, but you're free to pause the video and like figure that out and do the math to do that. Just look at the periodic table and count the molar mass of potassium ion element, chlorine element, and 3 oxygens. But if you do that, you should be getting 122.6 grams of KClO3. And now if we do this math out, we're going to find that you should be getting about 2.12 grams required in order to do this reaction. Now, does that make sense? I mean, it's a kind of small container, right? It's only 0.65 liters. It's pretty small. Temperature wasn't crazy high though, but the pressure wasn't super high either. So it at least seems reasonable that we would make only a small amount of oxygen given how small the container is. But yeah, that's pretty much it. Everything I want to talk about for Dalton's law. I'm thinking next I'll probably just do a video on the molecular kinetic theory. But if you have any questions on this topic or anything that I covered that you want some more explanation on, or even like the math itself, like please feel free to comment and I'll get back to that as soon as I can. All right, thanks for watching. Hope you enjoyed it.